In this lesson, we will discuss the greatest common divisor for two integers and the Euclidean algorithm for finding the GCD. Let's define the greatest common divisor for two integers a and b that we're going to assume are not both equal to 0. The greatest common divisor of two integers a and b not both 0 is the largest positive integer that divides both a and b. The greatest common divisor of a and b is denoted by GCD parentheses a comma b, or simply parentheses a comma b. Now, this expression occurs so often in number theory that it's the only function that has no notation. You can just simply write parentheses a comma b. And even though this looks like an ordered pair, like a point in the real plane, from the context, it will be clear that they were speaking about the greatest common divisor. Probably stick to using GCD A and B for our notation. Now, as a quick note, the GCD of any two integers A and B will always exist. Since 1 is a common factor of every integer, A and B always have at least one common factor that's positive, and the greatest common divisor of A and B is smaller than the absolute value of A or the absolute value of B. Every divisor of A has to be smaller than the absolute value of A, and likewise every divisor of B has to be smaller than the absolute value of B. So the greatest common divisor is always between 1 and the minimum of absolute value of A and absolute value of B. Let's look at some examples. The greatest common divisor of 120 and 36 equals 12. The largest positive integer that goes into 120 and 36 is 12. The GCD of 5 and 5 is 5. The GCD of 16 and negative 8 is 8. So every integer has positive and negative divisors. So for example, 8 divides negative 8, but also negative 8 divides 8. So the GCD of 16 and negative 8, you could really think of that as the same as the GCD of 16 and 8. Every divisor of negative 8 will also be a divisor of 8. So for example, if you had two negative numbers, like the GCD of negative 50 and negative 6, it's probably easier. We think about integers, usually in a positive sense when we think about numbers. So let's look at this as the GCD of 50 and 6. So what's the largest positive number that goes into 50 and 6? It's 2. What about when one of these numbers is 0? So the GCD of 0 and 10. So we're really not going to consider the GCD of 0 and 0. Some people define it as 0. So let's look at the GCD of 0 and 10. Well, every integer divides 0. But the biggest integer that also divides 10 is the number 10. Let's talk about two integers being relatively prime. So if two integers have no positive divisors in common other than 1, then we say that these two integers are relatively prime. So in other words, if the greatest common divisor of a and b equals 1, then a and b are relatively prime. Now this has nothing to do with whether a and b are both prime. For example, 6 and 35 are relatively prime. If you look at the greatest common divisor of 6 and 35, it would equal 1. But 6 and 35 are both composite. Here's some facts about greatest common divisors. What if I took the greatest common divisor of an integer a with itself? Well, without claiming that a is positive, we can just say that the greatest common divisor of a and a would be the absolute value of a. If you had two negative numbers inside GCD, you might as well just look at the GCD of positive numbers a and b. So the GCD of a and b will always equal the GCD of absolute value of a and absolute value of b. So usually when we look at greatest common divisors, you could just consider greatest common divisors of two positive integers or non-negative integers, but you don't have to. We also saw this fact that if you take the GCD of 0 with any non-zero integer a, that should equal the absolute value of a. Because every integer divides 0, and the biggest integer that divides a would be absolute value of a. Now we're going to look at the Euclidean algorithm for finding the greatest common divisor. Before I formally define the Euclidean algorithm, which is named after that famous Greek mathematician Euclid, I'm going to show you an example of how you find the greatest common divisor using the Euclidean algorithm, which is really repeated usage of the division algorithm. So I'm going to show that the greatest common divisor of 482 and 1180 equals 2. So first I want to divide 482 into 1180 using the division algorithm. Okay, so 482 goes into 1180 2 times, and that will leave a remainder of 216. So I can write 1180 as 2 times 482 plus a remainder of 216. Now I'm going to continue to use the division algorithm, but I'm going to start over with 482 and the remainder 216. So I'm going to divide 216 into 482. Well, 482, I can divide 216 twice into 482. So 482 is 2 times 216 plus a remainder of 50. And then I'm going to repeat. Now I'm going to use the new remainder 50. I'm going to divide it into the previous remainder 216. So 216 equals 4 times 50 plus a remainder of 16. Let's continue. So I'm going to divide 16 into 50. Well, 50 equals 3 times 16. 3 times 16 is 48, plus a remainder of 2. And if I do this one more step, we see that when I divide 2 into 16, I'll get a 0 remainder, because 16 equals 8 times 2 plus 0. Well, by the Euclidean algorithm, we'll see that the last non-zero remainder in this process actually equals the greatest common divisor. So in this case, the last non-zero remainder is the greatest common divisor of 482 and 1180. So the last non-zero remainder is the greatest common divisor, 482 and 1180. So let's be more formal about our definition of the Euclidean algorithm. So in general, let's just assume that A and B are both positive. So in general, to find the GCD of A and B, and without loss of generality, I'm going to assume that A is bigger than B. So we've already dealt with the cases when A and B are both negative. We also know that the GCD, if A and B were equal, would just be the absolute value of A. So really the only general case we need to consider is when A and B are both positive and one is bigger than the other. So without loss of generality, I'm going to assume that A is bigger than B. So here's how we did this. We're going to use the division algorithm repeatedly to find the greatest common divisor. So I'm going to start by dividing B into A. So first, I'm going to divide B into A. By the division algorithm, I can write A as a quotient, we'll call it Q1 times B plus R1, where 0 is less than or equal to R1, which is strictly less than B. Then I'm going to take this remainder R1 and divide it into B. So I can write B as a quotient, I'm going to call it Q2 times R1 plus a new remainder. Let's call that R2. And we see that R2 must be greater than or equal to 0 and strictly less than R1. So as we repeat this process, we see that the remainders are getting strictly smaller. Each time the new remainder is strictly smaller than the previous remainder, but they're also non-negative. They're also bounded below by 0. So after repeated steps of the division algorithm, eventually the remainder must equal 0. So let's continue. I'm going to divide R2 into R1. And we get that R1 equals a quotient, it's called Q3 now, times R2 plus a new remainder R3. And again, R3 must be greater than or equal to 0, but strictly less than R2. So eventually, the remainder will equal 0 because all the remainders are non-negative integers and they are decreasing. So if we continue this a few more times, let's go down to the next to last iteration of the division algorithm. So I'm going to divide, let's call it Rn minus 1 into Rn minus 2. So Rn minus 2 equals some quotient, it's going to be Qn plus 1 times Rn minus 1 plus a remainder Rn, and again this nth remainder is greater than or equal to 0 and strictly less than Rn minus 1. And so this Rn is going to be the last non-zero remainder. So in the last step, when I divide Rn into Rn minus 1, I will get Rn minus 1 equals quotient Qn plus 2 times Rn with remainder of 0. Then we claim that the greatest common divisor of A and B will equal Rn, the last non-zero remainder. So this is the Euclidean algorithm for finding the greatest common divisor. But why does this work? Well, in the last equation that we had, we saw that the last equation was Rn minus 1 equals a quotient Qn plus 2 times Rn plus 0. If you look at this statement, the greatest common divisor of Rn and 0 is Rn. So we've converted our first equation involving A and B to the last equation where all we have to do to find the greatest common divisor of Rn and 0 is look at Rn. The last equation, we see that the greatest common divisor of Rn and the remainder 0 is just Rn. So we actually have a theorem that we're going to use here. So the theorem says, we'll prove this theorem next. It says that if I can write A as quotient times B plus R, then the greatest common divisor of A and B is equal to the greatest common divisor of B and the remainder R. So in each step of the Euclidean algorithm, the remainder was getting smaller and smaller until it equals 0. So in the last step, finding the greatest common divisor is easy. So we'll prove this theorem next, but as we saw in the Euclidean algorithm, we started out with the greatest common divisor of A and B. And according by this theorem, this would equal the greatest common divisor of B and the first remainder, R1. That, in the next step, would equal the greatest common divisor of R1 and R2. And that equals the greatest common divisor of R2 and R3. And we continue this process until we get all the way down to the greatest common divisor of Rn minus 1 and Rn, which equals the greatest common divisor of Rn and the last remainder, which was 0. But we saw that the greatest common divisor of any integer with 0 is just Rn, which is non-negative. So if we can prove this theorem, then that justifies the Euclidean algorithm for finding the greatest common divisors. So here's our theorem. For integers a, b, q, and r, so if a, b, q, and r are integers, with a equal to qb plus r, then the greatest common divisor of a and b equals the greatest common divisor of b and r. So if we prove this theorem, then we've justified the Euclidean algorithm. So in this proof, we will show that all the common divisors of a and b are also common divisors of b and r, and therefore the greatest common divisor of a and b would have to equal the greatest common divisor of b and r. So let's start out with a common divisor of a and b. Let C be a common divisor of a and b. Then earlier we proved that if C divides A and B, then it will also divide any linear combination of A and B. So earlier, we proved that C divides any linear combination of A and B. But R is a linear combination of A and B because I can write R as A minus QB. So A minus QB is a linear combination of A and B, so therefore C divides A minus QB, which is R. Thus, C is a divisor of R. So if C is a common divisor of A and B, C is also a common divisor of B and R. Now, suppose that I have a common divisor of B and R. Let's call it D. Suppose D is a common divisor of B and R. Then D would be a divisor of any linear combination of B and R, but R equals A minus QB. So then D divides any linear combination of B and R, but I'm going to write R as A minus QB. But I can actually write A as a linear combination of B and A minus QB. So I can write it A as A minus QB plus QB. So this is a linear combination of B and A minus QB. And I said that D has to divide this linear combination. So D divides this whole expression. But if you see, if I simplify this expression, that just equals A. Therefore, D divides A, and D is a common divisor of A and B. So we have shown that every common divisor of A and B is also a common divisor of R and B. Therefore, the greatest common divisor of A and B must equal the greatest common divisor of B and R. So since every common divisor of A and B is also a common divisor of B and R, it follows that the greatest common divisor of A and B must be the same as the greatest common divisor of B and R. So that finishes the proof of this theorem, and it justifies why the Euclidean algorithm works to find the greatest common divisor. Let's look at another example of the Euclidean algorithm. Let's find the greatest common divisor of 12,345 and 11,111. So I'm going to start by dividing 11,111 into 12,345. So 12,345 equals 1 times 11,111 plus a remainder of 1,234. So now I'm going to take the remainder of 1,234 and divide it into 11,111. So that goes into 11,111 9 times. So this equals 9 times 1,234. And that's going to leave a remainder of 5. Now I'm going to take the remainder of 5 and divide it into the previous remainder, 1,234. So 1,234 divided by 5 is 246, with a remainder of 4. 5, when I divide it by 4, is 1 times 4 plus a remainder of 1. And once you get a remainder of 1, you pretty much can stop, because in the next line you're sure to get a remainder of 0. But just to continue this out, 4 equals 4 times 1 plus a remainder of 0. So the last non-zero remainder was 1. Therefore, the greatest common divisor of 12,345 and 11,111 is 1. And we say that these two integers are relatively prime. So they have no other divisors, positive divisors in common other than 1. In this last example, I'm going to show that the consecutive Fibonacci numbers are all relatively prime. Recall the Fibonacci sequence. Which starts off as 1, then 1, 2, 3, 5, 8, and so on, where the next term of the sequence is defined by adding the previous two terms. We can define this recursively by the rules F1 equals 1, the first Fibonacci number equals 1, the second Fibonacci number, F2, equals 1, and the nth Fibonacci number is defined as Fn minus 1 plus Fn minus 2. For n greater than or equal to 3. So it actually is a fact that consecutive Fibonacci numbers are relatively prime. So if you look at in the list so far, for example, 5 and 8. 5 and 8 are both relatively prime. 3 and 5 are both relatively prime, and so on. So here's the theorem we're going to prove. Consecutive Fibonacci numbers are relatively prime. So we said that two numbers are relatively prime if their greatest common divisor is equal to 1. So I'm going to use the Euclidean algorithm to show that the greatest common divisor of any consecutive Fibonacci numbers equals 1. So here's the proof. I'm going to use the Euclidean algorithm to show that the GCD of Fn and Fn minus 1 equals 1. Well, let's start with the first two Fibonacci numbers. The GCD of F2 and F1 is the same as the greatest common divisor of the numbers 1 and 1, which equals 1. So F2 and F1 are both relatively prime. Now let's assume that n is greater than or equal to 3. And let's look at the GCD of Fn and Fn minus 1. So I'm going to divide Fn minus 1 into Fn. But Fn equals Fn minus 1 plus Fn minus 2. And since Fn minus 2 is between 0 and Fn minus 1, this actually is the division algorithm for Fn minus 1 divided into Fn. So if you think about it, Fn will equal 1 times Fn minus 1 plus a remainder of Fn minus 2. Then I'm going to divide the remainder Fn minus 2 into Fn minus 1. But again, we see that Fn minus 1 will equal 1 times Fn minus 2 plus the remainder Fn minus 3. Well, if we continue this on, eventually we'll get down to dividing F2 into F3, and this will look like F3 equals 1 times F2 plus F1. And then in the last step, when I divide F1 into F2, I get F2 equals 1 times F1 with a remainder of 0. So the last non-zero remainder was F1. But F1 equals 1. Therefore, the GCD of Fn and Fn minus 1 equals 1, and we can conclude that consecutive Fibonacci numbers are relatively prime.